Now let's turn our attention to example number 5. I want to find a power series representation for this function, the natural log of 1 plus x, and ultimately state its radius of convergence. So again, I'm looking for a power series that can model what this function is going to look like. And that's really hard to do. I might notice that pretty much all the strategies that we used previously are not going to be very helpful. Specifically, this g of x does not appear to have a formula that resembles the sum of a geometric series. I don't see this as something close to an a over a 1 minus r. In addition to that, I don't see how I can start with maybe something that I already know, like we did in the last example, and simply take its derivative or antiderivative to get to where to get to this. So instead, I'm going to take a very different kind of approach. First, I'm going to go ahead and note the following. Oops. Okay, here's what I'll say. So first, we note that if I was to take the derivative of g, I would get the function 1 over 1 plus x. And this right away should be recognized as something really good. Because while this g of x function does not represent anything geometric looking, its derivative kind of does. With a little bit of manipulation, I can get this to look like a over 1 minus r. So again, I can say that this resembles the sum of a geometric series with a equals 1 and r equaling negative x, provided that the absolute value of my r is less than 1. That gives me the absolute value of my x is less than 1. And that, of course, gives me that x is between negative 1 and positive 1. So as long as I pick this kind of x, this g prime looks like a geometric series sum. So what we can kind of claim right now is that g prime of x, which again is 1 over 1 plus x, is going to be equivalent to the following series. So it's a series that starts from n equals 0 and goes to infinity, but it's geometric, and so it's got the form a times r to the n. And notice here, if I wanted to, I could go ahead and rewrite that a little bit. I'm going to do it here because I think it'll make it a little bit easier for what's coming in the next step. I'm going to take that power of n and I'm going to apply it to both pieces on the inside of those parentheses, so the negative 1 and the x. So this is the series that I have for g prime. Now notice, have I answered the question? No, I haven't answered the question at all. I found a power series that models g prime of x, and I know that it models it on the interval negative 1 to 1. Notice that has a radius of convergence of 1. But the question was, what happens with g? So how in the world can I use what I know about g's derivative to understand something about g? Well, you might have guessed it if you're thinking about the previous theorem. Maybe I could now do an antiderivative of what I found here, and that would make things a lot easier to work with. Now, specifically, when I do my antiderivative, I'm going to do the antiderivative of my function, and I'm going to do the antiderivative of this version of the power series, because I think it'll be a little bit easier to work with. Okay, so then I can go ahead and claim this. I can then claim, thus, g of x, which is equal to the natural log of 1 plus x, should be equal to an antiderivative, and take a look at how messy this notation looks. This should be equal to an antiderivative of this thing with respect to x. So if I want to go ahead and do this, it's not too terribly difficult. Remember that every antiderivative is going to have a c on it, and these I just tend to put it at the front so I don't forget about it. And taking the antiderivative of everything on the inside should be easy, because I just have to remember that if I want the antiderivative, this is a polynomial. The negative 1 to the n is just a number. Remember, n is just a number. It's x that is the variable. So if this was something like, I don't know, negative 2x to the 5, right? If that's what I had, taking the derivative of something like, or antiderivative of something like this is very simple. I raise the power by 1, and I divide by the new power. So it's not any different when I take a look at what I have here. Here I just have number times x to a number. So I'm going to go ahead and rewrite this as, oops, got to put in my series notation first. So I'm going to have a series, n starts at 0, goes to infinity, and I'm going to have negative 1 to the n. I'm going to raise my power by 1. Oops. And I'm going to divide by my new power. There it is. I have a series that works. So this is really powerful, and I know right away that my value of r is going to be 1. It's got to be the same as what it was before. Because remember, when I take antiderivatives or derivatives, I don't change the radius of convergence. So at this point, I'm almost finished. The only thing that might now need to be done is dealing with my answer here. Specifically, we would like to find C. So in order to help do that, I'm going to try to go ahead and think about, again, what it is that we've claimed over here about these two things being equal, and what exactly do I mean when I say I have a radius of convergence of 1. This is paramount. This will display to me how well you actually understand what you're doing, as opposed to just how to do it. So remember, if you were to type right now this natural log function into your calculator and hit the graph button, and then you were to type in this power series, like term by term, maybe you type in the first 50 of them, and then you hit the graph button again, these two things should look almost the same, but again, on what possible interval of convergence? Well, I'd have to first see where this is centered, and so I'd want to know what is being subtracted right now from x. Well, nothing's being subtracted, so this is centered at 0 with radius 1. So I have some options right now for my interval of convergence, right? This is kind of like what we had discussed in the last video, that I might have many different possibilities for what my interval of convergence might be. The endpoints can change, but the rest of it, the center at 0 and the radius of 1, that's the same. So here's what I know. Anytime I plug in a value for x on both sides, that is between these bounds, guaranteed, then I know both sides are equal. Not close, but identical. So I'm going to go ahead and pick out a value of x that I think is definitely inside my intervals of convergence, or my interval of convergence, regardless of which one it might be. And then I'm going to plug it into both sides to see what I come up with. So I'll say this. We see that x equals 0 is in the interval of convergence. Do you agree with that, right? Notice 0 is inside of every single one of these. So no matter which one of these is the right interval of convergence, 0 is inside. Thus, that means that if I go to g of 0, which is natural log of 1 plus 0, that should be identical to plugging 0 in for x on the other side. So that gives me negative 1 to the n. That would give me 0 to the n plus 1 over n plus 1. Now if I simplify some of this down, I'll see what I ultimately end up with here. Natural log of 1 is really just 0. On the other side here I have c plus the sum of, well, really just 0. And if I add up 0 a bunch of times, I just get 0. So of course I end up with here, c is the value 0. And so I can actually then make one final statement. I can say that our g of x function, which was our natural log of 1 plus x, that's got to be equal to, actually, just this series. The constant in front of it we found was 0. So I'll just go ahead and rewrite this out one final time. And there we have it. I actually have now a power series that models this natural log function. And I know it models it with radius of convergence 1, and I can see the center, so I know that these are still my possible intervals of convergence. So we've fully answered the question that we've had here. We found a power series representation, and we found the radius of convergence. This is a really cool process. Sometimes it's helpful to take the derivative of a function we're trying to model, find out how to model its derivative, and then kind of integrate our way back up. That's kind of a really, really interesting idea. And in fact, it's the exact idea that we'll need in the next question with example number 6.